Ladies and gentlemen, very warm welcome also from my side. I'm Dennish Gross. I work for a Swiss-based company called GeoBrook, and I like to thank NGS a lot, also Uttam and Suman, helping to make this event happen. And today I try to contribute some points on how GeoBrook or how we do slope protection, rockfall protection works in other parts of the world. Like to contribute because a lot of the things which I will mention have been mentioned before already. But this is of course because we are here geotechnical experts, so we talk about the same issues. So there will be two presentations actually. The first one, this one, will be dealing with slope protection, and the second one will focus a little bit more on rockfall barriers and debris flow barriers. So this is the agenda. You can see I will give a brief overview and background of where I'm coming from. I will raise some questions on stability problems, on the stability analysis. Then we will talk a little bit about hard, flexible and soft facings to cover the slope. Then I will introduce the system which we promote, the application we promote. I will lose some words on the Ruvolum concept, which is the dimensioning concept, which is behind our application. Show you a short case study and a couple of references worldwide. I put a lot of pictures. The company GeoBrook actually was part of a company founded in 1836, where they produced hemp ropes for the sailing ships. And then after the use of sailing ships declined, this company started to produce steel wire ropes to actually, well, what we still do today for cable cars or for structural bridges. And then by the mid-20th century, they started to invent or produce these very simple avalanche protection systems with two wooden posts and put a steel wire rope net in between to hold the snow. And during summertime, they recognized, okay, there are rocks in those nets. And that's where GeoBrook started to think of in the middle of the 20th century, okay, we have to develop those systems to actually create flexible rockfall barriers. But this will be then the second part for my presentations. The other thing is the material which we use is unique. We use a high tensile steel wire, and this enables us, which you will see now in the later slides, to do certain things. And for that, actually, I want to draw the attention of you. In the seminar package, you find this little flyer. And inside, you have two different kinds of wires. And I ask you to do now or to do later at home or in your office with your friends, try to bend those wires. You will find one of those wires can easily be bent by hand, without tools of course, which is a mild steel wire used for gabions, for example. And the other one is the high tensile steel wire. So this is almost all what I will tell you about promoting my product actually. We can see here the different kind of applications we can provide to mitigate geohazards. We will focus here on rock slope and soil slopes, and then in the second presentation on rockfall barriers. You might recall this sketch, a similar one from Shankar's presentation, and we'll have a look there at the debris flow mitigation. So stability problems. While I was preparing this presentation, I found this graph from Dave Pedley, who is a professor in England and the UK, but he's also doing quite a lot of work worldwide and especially also in Nepal. And you can see here the spread of fatal landslides in the last maybe 10 years. And this blue line here This is actually South Asia, and these lines here are Southeast Asia. So this is an issue. I think this is something we have to ask ourselves. Why is that though? Is this only because of climate change? Of course, earthquake, like the Gorka earthquake, has an important impact on those landslides. What can be other reasons? Informal road construction, for example, or simply the geological complexity that has been there before, ever since. So if we look at the general problem which we deal with, I'm not going into the detail here because this is a very simple sketch which we know all, but the main triggering effects, of course, are gravity and water. And I appreciate very much that also in the former presentations, almost each of you have been mentioning, take care of the water. Whatever design you do, if we forget about the water or underestimate the influence of water, this will create a problem, at least a problem, if not a failure. So a couple of slides to just illustrate more or less simple stability problems. This is from a project in Germany, slope failure due to water saturation. Then we have these type of failures on convex slopes, of course. And other problems, for example, can be that the stratification is unfavorably orientated. We cannot see here directly, but these sandstone beds, they dip all towards the road. So stability analysis. Before dimensioning, we are urged we need to do a proper site investigation. And if we don't have proper data, then we can discuss the factor of safety. So information needed from the site must be sufficiently understood. We need to know about the geometry now or also after we cut the slope. We need to know about the water conditions. And the geology, of course, has to be sufficiently understood. So this is also, we go quickly through that. There are a lot of different issues, that was too quick, which we have to deal with. Since, we are geotechnical experts, this slide is rather boring. So if we look at slope stabilization, I would say from our experience that we either deal with superficial instabilities, so a kind of superficial erosion or a superficial sliding plane, not too deep, which is actually the bigger part of the projects, or we deal with deeper seated sliding surfaces. If we deal only with superficial instabilities, then, for example, our Ruvolum concept or the design software is capable to provide a design concept, give you a nail pattern, nail distance, nail length. Whereas in cases where we have deeper seated sliding surfaces, we will have to analyze the global stability first. There are various commercial available programs to do that. They have different theoretical models behind it. We mostly use a Bishop circle, but there are other circle types and models which you can also easily use. So for deeper seated sliding surfaces, first we would do a global stability analysis and then investigation of what happens between the nails. And for superficial instabilities, we would go with an analysis of the slope with this Ruvolum software. This is just a different force transmission. This is an issue we face, or I face very often, that there is, even in the geotechnical society, not of Nepal I would say, but in general, globally, there is sometimes a little bit of confusion about what we are talking about. On the left-hand side here you can see this is an anchor, which is a real anchor. It's a pre-stressed anchor. That means we only mortar the bottom of the anchor, of the rebar, of the strands. And this, of course, then has to lie behind the sliding surface, which you can see here. Also, then we have the free anchor lengths, and you can see here also that there is a very high load or force at the head of the nail then. That's why, for example, we do those pillows at the nail of at the head of the nail. Whereas in most applications, when it's about the slope protection systems I'm talking about, we will use nails which are fully grouted and will transmit the force, the load through the skin friction. And here, the load at the head of the nail is smaller. Sorry, it is smaller than in an anchor case. So this is something I find very often. I find there's a little bit of confusion. Are we talking about anchors? Are we talking about nailing? Then if we talk about the foundation of rockfall barriers, yeah, we anchor them, but in fact they are micropiles. So this is something to keep in mind, I think. So when we talk about the facings, we can diversify into basically 3 different kinds of facings. We have hard facings, mainly dealing with any kind of concrete structure. We have those soft facings, which are generally, for example, geosynthetics. And we say we have those flexible facings, which are all sort of different kind of meshes. So with the hard facings, shotcrete is one of a very widely applied method all over the world. The problem with the shotcrete is, from my perspective, very often that we cannot see or we cannot control what the water is doing behind the facing. And even if we put the drainage pipes according to the design, have you ever been trying to do maintenance on those drainages after 5 or 6, 10 years? So depending on the fine-grained material behind the facing, this is going to be a difficult issue. So here you can see also one of a typical shotcrete failure. Other hard facings, for example, are those concrete grid beam solutions, widely used in Japan. You can find them in Taiwan, for example, or in other countries all over Asia and also South America. Problem what I see with them is, for me, they are extremely time consuming. To build all those formworks and then reinforce it properly, that's extremely time consuming and costly. And another disadvantage from my point of view is just that it's a brittle structure, and especially in earthquake prone areas, they are very vulnerable. So I have one, I would almost say nice example, but I don't like the expression nice because it's dealing with this Fukushima earthquake. Both those projects are in the Fukushima prefecture, and you could see here on the left-hand side, you can see the failure of this concrete grid beam structure, and here on the right-hand side, you can see you can see both devastation and also this techo slope, stabilized slope with high tensile steel wire mesh, which is still intact. Soft facings, geosynthetics in general, very good for erosion control, for slope stabilization, rather not. And then when we come to the flexible facings, there are a couple of older systems, and also this picture here, or the pictures you can see here, is from a system which has been introduced by Geobrook in the 80s, which uses mainly wire ropes. The main problem with the wire ropes is that, again, it's very time consuming to install, and you are pretty much bound where you put your anchors, because the nail pattern has to comfort the mesh panel size you use, which is, from a geotechnical perspective, a big disadvantage, because I want to put the nail where I think it's necessary. I want to put the nail in intersections or under overhangs, actually. So when we talk about high tensile steel wire meshes made from GeoBrook, this is a mesh family which we call TECO. It's basically consisting of 3 components. It's the steel wire meshes with different openings and different diameter of the single wire. You can find a couple of samples when you leave the room on the left-hand side on the table. There are different kind of bearing or spike plates, how we call them, which sit on top of the nail. And there are these connection clips, also made from high tensile steel wire, to connect the mesh panels. Like that, we are able to create an homogeneous area of material with the same strengths, and we can place the nails according our geotechnical requirements everywhere in the area. Additionally, of course, we need nails. Here also, we have the usual rebars. Let's call it rebar. It's effectively a rebar. But especially in the soil conditions, self-drilling nails, or so-called hollow bars, are recommended, because it makes it much more easy to drill and grout the hole in the same time, rather than to fight with collapsing holes before you can insert the rebar or the grout pump. So as a summary, for this TECO system, there's a static function, which you will only learn in the slides afterwards, using high tensile steel wire meshes. We have a very high bearing capacity with those meshes, of course. It can be pre-tensioned against the slope, and it can be dimensioned. So this will be the next part. I will talk a little bit about this RuVolum concept. This is the name we have given the baby, this software, or this dimensioning concept, which is an online software. So if you are interested, you can register on the GeoBrook homepage. There are no costs or anything involved, and try to work with the software. So basically, RuVolum investigates the superficial instabilities, and it will basically investigate those 2 cases, which you can see here. One is the investigation of the local instabilities between the single nails, and the other one here on the right-hand side is the investigation of the slope parallel superficial instability of this unstable layer here, the yellow one. These are the sandbox tests we have been doing, or not the tests, but the sandbox studies we have been doing in 2000, actually to learn more about the deformation and at which places which deformation takes place. In 2015, we have been doing that in a one-to-one situation with this large sandbox. So this is filled with material. There's a mesh on top, there's some nails. We do laser scanning to measure the deformation. There are strain gauges in the nails to measure the load there. And I will show you 2 or 3 more slides of the results after this part. So this is going back to the investigation of the instability between the nails. You can see here, this is a limited equilibrium equation, investigating the stabilizing force which we need to stabilize the materials here in between. We will take into account the cohesion, the volume weight of the material, of course. And I want to draw your attention shortly at this side where we look at the slope. So the red points, the red dots are the nail heads. Because if we look at this cross section, we will apply pre-tensioning force on the head of the nail, on the spike plate, of 30 to 50 kilonewton. And this pre-tensioning force actually will neutralize part of the weight of the dead body between those nails, which enables us to widen the nail pattern. We don't have to stick to a 1.5 or 1.8 meter distance nail pattern, because we will stabilize some of this weight already with the active pre-tensioning. So then we have, at the end, we have here then two decisive mechanisms or forces. One is the proof of the mesh against the shearing off here. And this is why it's so important that we use a high tensile steel wire mesh. And so we don't have experience of puncturing here. And then, on the other hand, we have this force Z, which is the proof of the mesh for the selective transmission of the force. The second investigation, of course, relating to the slope parallel superficial instability, I think we already see that the decisive point, if the unstable layer is getting big enough, the decisive point will only be here the shearing of the nail, also the diameter of the nail. Also, in that dimensioning concept and in the software, you can introduce a load case of earthquake simply by increasing the weight of this dead body with the acceleration factors of the earthquake or of the assumed earthquake. The same, of course, then can be done with streaming pressure with water influence in the slope. I have a quick case study of a project in Colombia in a place called Cali. We can see here a residential building built in 1995. You can see the slope here behind. And very soon after the people moved in, they started to have issues with that slope. So that was in 2007. And then in 2008, the retaining wall in the backyard gave way. And then in 2009, one of the residentials, of the remaining residentials, because a lot of people moved out already, he took this video from his balcony of the ongoing collapse of the slope behind them. And this is only after that event that the client actually, the client and the consultant approached us to develop a proper solution. So this is again a very nice example of geotechnical know-how, or geotechnical engineers get very often only involved into the project when a failure already happened. It's not very often that we have a video of the failure of the slope, which we can treat then afterwards. We have been done trimming of the slope, of course, first. Then also here they drill with the use of scaffoldings. At the instruction on the site this was the first project ever in Colombia, so we had to send people to instruct the contractor how to do it properly. And this is then how it looked in 2011. People moved back in, all fine so far. A couple of pictures of a couple of projects all around the Asian region, where you can see different applications on roads, like here in the Philippines. This is a limestone a project in a limestone cliff, or limestone geology. This is the very same, just pictures from a drone. Then here we have a project where you can see there is a kind of bedrock, but we also had to retain the colluvium lying on top. This is the very same project. All those projects, especially in areas where there's a lot of rain, we will recommend or advise to use hydro seeding afterwards, so we have a quick revegetation of the slope, which on the one hand side, of course, will make it look nicer. On the other side, it will enable us to have a certain control of the surface water also. And of course, the small roots will also contribute to the stabilization of the first 10-15 centimeters of the slope. Another project here during excavation. Not always are the conditions like that it's so easy actually to install it. You can also see that the drilling machines they use here are lightweight drilling rigs, which are very easy to move over the slope, so this will also save time during installation. One more project from the Philippines. Since the Philippines is within my responsibilities, a lot of pictures are from the Philippines, I'm sorry. We have this big project we have been doing in Mindanao on the Philippines with this superficial erosion here of these very weathered andesite materials. This is the very same site and just after completion. Then I can also show you some pictures of a project in Vietnam. So this is a relatively small site. The height is maybe like 15 to 18 meters only in a rock environment. And we have this rather high slope where there was initially a shotcrete installation, which you can still see here at the side, which failed. And then we covered the whole slope, including the shotcrete, with one of the high tensile steel wire meshes. It's just another perspective. Small project which we have been executing in Indonesia, like but almost 90% steep in a very different geology. So this is a volcanic deposit which is called lahar, which especially in connection with water can be very unstable. And a couple of examples which had been executed just here in the neighboring India. One of Kiratpur-Nachok Expressway. Also those pictures derived from the same project. And one project which is still ongoing on Mumbai-Pune Expressway, where they use not only small mobile drilling rigs, but also drill from those platforms which are hanging on the cranes. So I come to the end of this presentation, and then I have a short video as a summary. So this is the online software which you can see here. This is one project in an abandoned mine in Brazil. That one is in Germany. Here you can also see the effect of hydroseeding. Thank you very much. So in this second part, I hope you are still not too sleepy. it's almost 6 o'clock. We will deal with rockfall barriers and debris flow barriers. So Shankar already mentioned or introduced rockfall barriers. This very picture here is in Nepal. So this is the first Jubrook rockfall barrier project which we have been doing in Trisuli. So in this first part, we will shortly talk about the rockfall phenomenon. I will give a brief introduction about how rockfall barriers look like. I will show you a case study here and a couple of examples, and then we will do exactly the same for debris flow barriers. So the rockfall phenomenon, I mean, this we are very familiar with. And also, if you look here on the right side, at a certain extent, we have to realign the road and we have to resettle people because it just doesn't make sense anymore to deal with certain quantities. When it comes to rockfall mitigation, we need to have something to protect. In this case, a road, but it can be a powerhouse or any kind of infrastructure. What we need to determine, and this is very vital, we need to find a trajectory, or at least we have to define a couple of trajectories where we expect that rockfall will happen. Also, very decisive is the size of the boulder, but not only the size, but also the geometry, because boulders of different geometry will behave differently in the rockfall simulation and also in the field. So you can see here we have to select or define certain geometries. You can see here on the left hand side this is a 2D rockfall simulation, and you can see here in the middle part this is a 3D rockfall simulation. So we also need to know not only the trajectory and have a cross section, we also should have data on what is the subsoil conditions over this trajectory, because the boulder will behave very differently if it hits a bedrock or if he hits a colluvium sitting somewhere there in between, or whether he hits, for example, a couple of trees. I had to include those because I was also twice, I think at least twice, I was visiting Sita Baba, where we did these 3D rockfall simulations actually. So we have been able to find a company by the help of Uttam and Deepak to produce 3D models with drones. Then we have been implementing the 3D models, and we did various RAMS rockfall simulations. And at one point we abandoned the project because we have been investing already a lot of time. And then we learned DOR is looking into the tunnel solution. Okay. Tunnel is also geotechnical engineering. Yeah, but rockfall simulations, we will receive data such as energy over at all the places of the trajectory. So we can sometimes even decide, okay, it doesn't make sense to put the rockfall barrier here. We have an easy accessible area here, we can put it here, and those rocks from this cliff, they won't reach the lower ground. Also, we will receive data as the bouncing height of the rocks, which is very decisive, because if we install a rockfall barrier which is 3 meters high and the bouncing height is 5 to 6 meters, doesn't help a lot, also except that we waste a lot of money there. All this data can also be used, of course, to do rockfall risk assessment, risk management. Here, I actually want to draw your attention to charts like this. So the chart here on the right-hand side, it's from the Austrian Service for Torrent and Avalanche Control. It's an Excel sheet, provides a very, very effective, but of course basic means to define different zones of risk. which is data which might help the client to decide, okay, this is the most prone area where we have to budget money first. We don't have money to do everything. So, but then we can tell them, or with the help of those risk assessments, risk management, we can help them and tell them, okay, these are the most prone areas. You need to budget money here first. And in this area, yes, there is a certain risk, but not as much as compared to the other sections. So you can allocate money maybe in 3 years. Also, this is one of the slides where I have to point out again why it's so important also in rockfall barriers that high tensile steel wire is involved. We have been not only successfully testing, but also now installing rockfall barriers with a kinetic energy capacity of 10,000 kilojoule. So this is a block of 25 tons falling from 42 meters height. And that means that this energy, well, the deflection which we have been talking about, or Shankar has been also mentioning, will be in this case for this barrier 8 meters. And it means also that within 0.5 seconds, the mesh or the barrier actually has to dissipate energy of 290 tons. And this is why high tensile steel wire meshes are important. Okay, short resume, stabilization versus protection. On the one hand side is what we call active protection with soil nailing plus meshes. No maintenance required afterwards. What you have to keep in mind that it takes longer, of course, for installation time, and if you have huge areas, it's not economical anymore. Then you could move to protection through rockfall barriers, because there you only have to install a single line, which is done quickly and which will cover or can cover a bigger area. I'm very happy that actually I can skip this because Shankar also showed this slide how rockfall barriers look like. There are posts installed on base plates which have a foundation, which are anchored. There are certain retaining ropes, and in between you find either this big brother of the Teco family or those ring nets made from steel wire, high tensile steel wire to retain the rocks. I skipped those because I think I will be running out of time. This is a nice short video which I want to show you about one of the tests in those canopy situations, which Shankar also mentioned earlier, which is self-cleaning in this part. But those barriers, those canopies as we call them, or yeah, it's like a rock shed actually, they only work until a certain energy. So well above 2000 kilojoule, we haven't been able to do it until now. But for the lower energies, they work very well. Of course, you cannot have any infrastructure below the road you want to protect, for example. What is or might also be very important for the client or also for a tender, that those barriers are specified according to certain guidelines. There's a couple of guidelines. One of them is a Swiss guideline, there's a European guideline, there is an Austrian guideline. They differ in certain details, but in general they define a quite good quality level of guide barriers. Also, what we do very often, or we need to do very often, especially when we come to customized projects, that we do those simulations with finite elements. Mostly we use Abacus, for example, one of the other of you might know, to actually see where are the highest loads in the mesh components or in the components of the barriers, which you can see here in the yellow or orange colors. The next one is the next one is showing the influence of different rock shapes. We have here a rockfall. It used, I mean, this is a research project with a Swiss research institute. This is a disc shape rock who behaves totally different than, for example, a spheric type of rock would behave. And this is a very important issue where we actually, as GeoBrook, together with research institutions, want to push more. So we have more testing under real nature conditions and not just a test in some abandoned quarry to actually compare different kind of barriers, but to learn more about what happens if a different geometry of boulders hit the mesh or the barrier not only in the center but also in the outer fields, or not only in the center of the center field but also here in the left corner, on the right corner, and this is a very challenging issue. Additionally, the WSL, they take data from these experiments to improve these RAMs, this 3D rockfall simulation program. So we are looking forward to the results in the near future there. Case study on rockfall. I choose a project in India, which is the pilgrimage route to Vaishno Devi temple. So you can see here, this is the pilgrimage way. It's one of, I think it's the second most visited pilgrimage site in India. You can see these simple structures to protect the pilgrims. And the authorities of the shrine actually contacted us back in 2015. And since then, we have been like almost every year, we have been adding some rockfall barriers because their budget is also allocated over several years. So you can see here, during the installation, two guys here erecting a post. Quite challenging environment, absolutely, to install a rockfall barrier at this position. And you can see down here the track and some of the rockfall barriers over it. A couple of rockfall barrier examples. An example from the Philippines. This time it will be only one example from the Philippines, because we mostly do slope stabilization there rather than rockfall protection. There's one example from Grasberg, which is a the biggest gold and copper mine, open pit mine in Indonesia. So they have their facilities down here. They have frequent rockfall. Once a rockfall happens, the regulations say stop operation. They lose millions a day. So that's why they are very much after it to have proper protection. And you can see here one of the boulders which has been retained in this barrier. Other projects from Hong Kong, where we have been installing barriers since more than 30 years now. And again, this project, this picture from Nepal. This was done to actually protect the Trisuli 3A. And it's also in the upper part, but I didn't have any nice pictures. At the very top of the slope, we did also some installation of techo meshes, but I like the good pictures, and it's not very easy to get there. I mean, I don't mind for the 5 hours drive, it's the hike up to the top. So also to conclude this part, actually I haven't done that video and I haven't asked for permission, but this is a short video I was sent from Nepal on that Trisuli 3A project. So I hope there will be nobody coming after me. Yeah, they built a small ropeway also to get materials more easily to the top. and we installed the barrier also by help of the helicopter because it's not that easy to access the site. This is the upper part of the slope with the taco mesh installation. And this is definitely a site where they have active rockfall. Again, you might remember this graph. So now we are not on the rockfall side, but we're getting to have debris mixed with water. We have been also developing dimensioning software here. The difficult thing about it is that you can either have mud flow like debris flows, or on the other hand, very granular flows. So this is quite a challenge, or was quite a challenge, to find the good, the valid design parameters actually to create the software. Also in Switzerland, we suffer a lot from debris flows. We have a lot loose materials in the Alpine mountains, lots of gravels. We have no monsoon rains, but we have a lot of strong rains too, which then will finally result in debris flows. And of course, the destructive energy of those debris flows is amazing. Whenever you see the results afterwards, it can be really devastating. So some of the protection measures, for example, have been the construction of big earth dams, or those concrete structure with these steel structures to retain the coarse debris, or those sabo or concrete dams, or sometimes also after been executing these risk maps. There has been also cases in Switzerland where we had to do evacuations and resettle people in other areas. Or, for example, also possible is the installation of those flexible debris flow barriers. Again, that was kind of similar to the avalanche barriers, where then back in the 1950s they discovered, okay, they might also retain rocks. We had a rockfall barrier actually in Japan, and in the beginning of the 90s, there was a major debris flow retained by these rockfall barriers. That's when we started to think, okay, we have to develop this further, because it's a totally different dimensioning concept behind the debris flow than behind a rockfall barrier. We have two types. One is the V barriers, the other one is the U barriers, and this just is derived from these geographical terms for different kind of valleys. And so the VX will sit in V-shaped valleys without any posts in between, and the UX barriers will sit in U-shaped valleys, and we will add posts in between. This is a small video, if it works. Didn't want to hear the sound, but there will be a second video afterwards. So here you can see different load cases which we had to take into account, or which you have to take into account when you deal with the debris flows. And you can see this is very unlike a rockfall event where you have one dynamic impact, even though it might be a couple of instant impact. Here we have to either cope with the increasing pressure of the debris, so we have to stop the debris flow. Then we have this filling event in the barrier to retain the materials in the barrier, and then afterwards we might have, well, such called overflowing events, when a second or a third surge of the debris flow will go over this barrier installations. So a couple of pictures how they look when they are filled. Here, that one. What is the height here? The height here is 6 meters. So it's a considerable amount of debris which you can actually retain. But of course, this is governed about because of the geometry and the inclination of the riverbed behind the barrier, upstream the barrier. Also, this solution we have been testing together with this Swiss research institute, the WSL. Quick case study again. I will take you to Peru, to a place called Chosica. It's not too far from Lima. We have again here a video from 2015 showing the impacts of massive debris flows on the village or on the small town of. Now the debris flow actually starts only. And there's a couple of gullies all leading to this city, so we only have this video. Here it goes. So again, there have been retaining structures here, and I think another one was over there. The authorities had to rethink about their concept, so they wouldn't again install those concrete dams, but we have been able to, together with our Colombian partner, Peruvian partner, sorry, to install 22 barriers here, actually. But you can see Chosica down here, and there's like 4 or 5 gullies going down to the city of Chosica. And we have another video during the recent event where you can see the filled barriers here, and they still experience water in the streets with some debris, but not to the extent which you will just also see, not to the extent like in the previous video. So you can see the barriers here filled up until the top. And still water here on the street. Huh? Of course, I mean, we don't stop the water. The water has to go somewhere. Our main issue is we have to collect as much debris, as much of the boulders that we can get. So the previously empty barrier now all filled up. Couple of examples again. I believe debris flow barriers, they also might have, or they for sure have a potential here in Nepal. There are a little bit different applications. For example, here we have been protecting, the consultant was afraid of ongoing erosion in the riverbed. So we installed a series of barriers. We will not be cleaned. I'm almost finished. Thank you. Which will not be cleaned, just to protect the riverbed from further erosion. Another example, for example, is this, where this check dam, which you can see here, the foundation was scored, and the consultant was very much afraid of failure of the whole dam. So we installed these barriers to collect debris to protect the foundation again. And one last example here from the Philippines again. And with this last slide, I conclude my presentations. I would like to thank you very much for your attention. And I give over to you.